This section is on parallel circuits. A parallel circuit is one with several current paths whose total current equals the sum of the current in each of the branches. So for example, if I were to draw a schematic diagram, I could draw one that looks like this, where each of the branches look physically parallel to each other, or I could draw it in another way and show the current coming out and then splitting into the branches. This would represent the same circuit in which 3 light bulbs are in parallel with each other. Now the current splits, and each of those 3 branches would add up to the current that's going to go through the battery. And the same thing here, each of these 3 parallel branches would have the same total current that's going to run through the battery. Now you probably will not be asked to find the total voltage because a parallel circuit has the same voltage drop or electric potential difference in each of the branches. However, if it does come up, you can always use Ohm's law. For a parallel circuit, the equivalent resistance is found a little bit differently. We're going to be adding the inverses of each of the individual resistances and then take the inverse of that answer to get our actual equivalent. So it looks kind of like the mirror lens equation, that 1 over F1 that we did earlier in the year, except now we're finding resistances. And the equation for the sum of the currents is really simple. We would take the current in each of the branches and add them together to get the total. So I have a practice problem for you. We've got 3 resistors that are connected in parallel across a 120 volt battery, and we're asked to find the equivalent resistance of the circuit. Now this voltage that's given is extra information. We do not need it. So we're going to use our equivalent resistance equation for a parallel circuit. So I've got resistors A, B, and C, since there are 3 of them that are given. Remember, you can add numbers in any order, so it doesn't matter which one of these are resistor A, B, and C, but I'm just going to plug in those numbers. Now remember, there are a few different ways you can type this on your calculator. One, when you type that in, you could do parentheses 1 over 330, and then close the parentheses plus, and then open the parentheses again, and type in that inverse, and then plus 1 over 220. Or in my calculator, I can type 330 and then hit the x to the minus 1 key, and on my calculator it'll show up as 330 inverse, and then I could do that for each of the other 3 resistor numbers. So on your screen, it would look like this row. And then when you hit enter, you're going to get a decimal. And remember that this decimal number is actually equal to 1 over the equivalent resistance, so we do need to take the inverse again. You could do 1 divided by the answer, or you could simply hit that x to the minus 1 key and your screen would show up as answer to the minus 1. So once you hit enter, you will get a final answer for the equivalent resistance of 106.8, and then remember that resistance is measured in ohms, so include your units. Now you can try one. We've got 2 resistors that are 68 ohms and 2 resistors that are 33 ohms, all connected in parallel with each other. You don't have to draw a schematic, but I'm going to do one for you just so you can kind of visually see what that looks like. So each of the 4 resistors are in parallel with each other. Now you're asked to find the equivalent resistance, so again, the voltage that's given to you is not needed. But since we have 4 resistors, that means we're going to take into account 4 of those inverses in our equation. Now the order is not specified, and they're all in parallel with each other, so you can add these up in any order and assign all 4 of these resistors to each of the 4 spots. So go ahead and plug those in and try it on your calculator and come back and check your answer. And when you do that, you should see that you get an equivalent resistance of a little over 11 ohms. So remember, once you add all of those inverses together, that decimal number is equal to the inverse of the equivalent resistance, so you do have to take 1 over that number to get your final answer. So I have one last example problem that's going to use a parallel circuit, and we'll talk about resistance, current, and voltage for this entire circuit. So I'm going to walk you through all these steps. So what I did was list everything that's given in the problem, the three values of my resistors and the voltage, and then I drew a schematic so I could visually see what's going on. Again, the order doesn't matter. I just did these as A, B, and C, listed in the order that they're given in the problem. So if you want to take a moment and draw that, go ahead. So for part A, we are asked to find the current through each branch of the circuit. One thing that's really important to remember is that each parallel branch has the same voltage drop or electric potential difference. So I made you a note. This is kind of the opposite of series circuits. In series, the entire circuit had the same current, but different voltage drops depending on where you were in the circuit. Well, in parallel, the voltage drop or electric potential difference is what's the same, and then each branch will have a different current. So we're going to use Ohm's law to find out how much current is in each branch. So to find out the current in branch A, I would simply rearrange Ohm's law and say the voltage over resistor A. And I can plug those numbers in, and when I go to do that, I see that branch A has a current of 1.5 amps. Now we can do the same thing for each of the branches. So go ahead. For branch B, I would still use Ohm's law. The voltage is going to remain the same, but I'm going to replace the resistance with resistor B's value. And in this case, that's going to give me 90 over 30. And when we divide that out, we can see that branch B has a current of 3 amps. So see if you can follow the pattern and find out what the current is for branch C, and pause the video and come back and check your answer and see if you got this correct. Okay, so you should have plugged in 90 over 20, and that tells us that branch C has 4.5 amps. You should also notice that the larger the resistance, the smaller the current, and then the opposite is true. The smaller the resistance, the larger the current. They are inverses of each other because the voltage is remaining constant. Next, we're asked to find the equivalent resistance in the circuit. We only have 3 resistors, so we're going to go back to that equation that we practiced with in the previous 2 questions. Go ahead and plug your numbers in and come back and check your answer. So once we do that, we see that 1 over the equivalent resistance should give us 0.1, and our actual equivalent resistance would be 10 ohms for this circuit. And lastly, we're asked to find the current through the battery. What this means is the total current for the circuit. And when we think about that, I made you a little note right here that the equivalent resistance of the circuit is the same resistance that's going through the battery. So if we were to choose to use Ohm's law and find that current through the battery, we would want to take the voltage of our source, which is the battery, and then divide it by that equivalent resistance that we found in part B. So I could do that and plug those numbers in, and I would end up with 9 amps. Also, I could have found this in an alternative way. Remember that for a parallel circuit, the current in each of the branches adds up to the total current that's going to go through the battery. So I simply could have added the current that we found in each of the branches, plug those numbers in from that part A question, and added those together, and I would still get 9 amps. So there might be an occasion where you can solve a problem in more than one way. If that's the case, then that might be a good idea to go ahead and look at both methods on your test, and it's a good way to check your answer because you should get the same result either way. That's it for parallel circuits. Next time, we're going to combine series and parallel together.